Hi, my name is Bryce. This is Lab 5, Magnetic Braking with Faraday. These are all the fundamental principles like Ohm's law, Faraday's law, and then relating them all together with flux, and then the time derivative of flux. And this is the Biot-Savart law in general form, magnetic force on a loop, stuff like that. These are just equations that we used. These are the results. The experimental time I got, the average was 1.26, the computational model was 3.22, so kind of far off, but not like super far. This is the initial conditions. This is of the bar magnet, the mass, and this is the mu I calculated in lab 3. This is of the aluminum tube, foil tube. The experimental stuff was the system was the aluminum tube and magnet. Everything else was surroundings. So the steps were to find the magnetic north of the magnet, which I did in lab 3, and I had labeled it. And then hold the foil, the aluminum foil tube like this, and the bar magnet at the top, so that way it can fall. And then drop it and have a friend record it each time, which I did, so I can see how long it was in the tube and take the average of that. Did it 5 times. The model was the magnet, which was a magnetic dipole, so it was that. And then the aluminum foil was representing loops of current through which the magnet would fall, so like going down through there. Uh, the assumption was the air resistance was negligible, basically, and that gravity and the magnetic force from the induced current on the aluminum tube were the only forces acting on the falling magnets, so that way it could be in free fall, which is probably why our computational model was longer, because it calculated those were the actual only forces versus other forces acting on the magnet, causing it to fall faster. This is the code. These are just the physical constants, out of 4 pi, stuff like that. Here's the measured values I found. And then the rest of the code was pretty much like left alone because it was generating all the picture stuff. And then this is the graph that was from my data. And you can see gravity's acting really quickly, causing it to fall fast. And then the induced current starts pushing really hard against, well, not really hard, but like counteracting gravity. So that way it's in a free fall. So no changing velocity, constant. So zero acceleration. And then here is how long that's what I found, how long it took to come out the tube. And then this is as it start, like it would start up here, and then the colors would just move down to show you the direction of the induced current. And that's what we talk about here. The intensity of the colors shows how like much current there was, I guess. So up here would be really high at first, and then the red was a counterclockwise current, which makes sense because it was on the bottom, and a counterclockwise current like that indicates a magnetic field going that direction, so that would be forcing it back up to counteract gravity. And the blue was the clockwise current. What happens to the dynamics of the system when you flip the magnet? It would be the same because the magnetic force is still increasing downwards. How does the total time in the tube of the real world system compare to that of your computational system? The computational system only accounted for those two forces, gravity and then the induced current, whereas the real model had actual other forces probably acting on it. And how to make it more accurate? Probably also when I calculated in lab 3 the mu of the bar magnet that I have, I could have calculated a little better. And then what does the shape of the velocity plot tell you about the forces? Well, at first it's falling with an acceleration, and then it reaches constant velocity, zero acceleration, and then it falls out of the tube. What if the resistivity of the conductor was reduced as close to possible to zero? Because in the code, we had to account for the resistivity of the aluminum, which is right here. And what if it was basically zero? That would mean that it would probably be closer to the computational model because the current would have no resistance, and so therefore it could immediately act. Um, how did the dynamics of the magnet falling change? It would probably change. It was probably fall slower and closer to free fall instantly. Um, and what if holes or slots are cut in the tube? How would this affect the ring currents in the model? Well, if holes were cut into the tube to make them more like rings, you would have the magnet falling through the ring, and as it's going through the ring, it would have a force acting on it when it gets out. There's really not a force as much, I guess, because you're not in between in the middle of the ring, so it's not as strong. So it might increase speed until it reaches another one, then decrease speed, increase, decrease, kind of like that. And then some possible errors are air resistance, and then error from the lab 3 when we were determining the mu of the bar magnet. Thank you.